All right, hello and welcome back to your Organic Chemistry 1 lecture. We are heading into the very last bit of the semester. So in this lecture, we're going to introduce alkynes. This lecture is going to start chapter 9 in the third edition or chapter 10 in the second edition, depending on which book you have. So just make sure you're following along in the correct chapter. We're going to talk about alkynes, what they are, where they come from, how to name them, and then, of course, we're going to talk about their reactions. Now, unfortunately, a lot of what we talk about with alkynes is analogous to something we've already learned with alkenes. So hopefully this will go a little bit quicker than the last chapter. After this, we have one last chapter, which is it's chapter 11 in the third edition book, and I believe it's chapter 12 in the second edition book, just on how to solve multi-step synthesis reactions. And that's a very quick chapter. So that one we'll go through in probably about a half hour, very short video. And that's more like giving you some background on how to solve some problems. So, and then we're done with the semester. So we'll be ready for the final exam review. So, okay, so let's not get too far ahead of ourselves. We still got to learn about alkynes first. So alkynes, just like it sounds, these are going to be related to alkenes and alkanes. It basically goes alkanes, all single bonds. Alkenes have a carbon-carbon double bond. Alkynes have a C-C triple bond. So that's what we're looking at here. So the two carbons that are involved in the triple bond are going to be sp hybridized so that they form a sigma bond with their two sp orbitals. And then there's going to be two sets of pi bonds. So in this case, you'd say this is like the py orbital, this is the px orbital, and they clearly pi overlap. So you get two separate pi bonds. So hopefully it makes sense. You've got a sigma bond and then two pi bonds. That's a triple bond. So because of these pi bonds, basically the area between the two carbons and above and around basically those two carbons is highly electron dense because of all those pi electrons. So basically those alkynes can act as very strong or moderately strong, I should say, nucleophiles. So basically like a lot of the reactions that we saw work with alkenes, those are all addition reactions. Those are going to work again on alkynes with some tweaks to the mechanism, of course, but gives you kind of an idea that this pi bond system can be used as a nucleophile. So alkynes do show up in nature every so often. Acetylene is the simplest one. That would be ethyne. It's just two carbons that are triple bonded to each other. So acetylene, you probably have heard of that in the form of acetylene torches. Um, so basically, they burn at a very hot temperature. If you mix it with, acetylene and oxygen, you get a very flammable type of gas that burns very hot, and so that's very useful for things like blowtorches. Additionally, there are a lot of times alkynes are very useful as kind of precursors. So we'll see how they're used in synthesis later on this chapter. And you'll just see that there's one reaction in particular that basically allows you to build out bigger and bigger molecules using alkynes. And so it becomes very important for synthesis of all kinds of organic molecules. Now, they are also present in biology, but not to the extent of alkenes and definitely not alkanes, because basically these alkynes are very high energy compounds. So they tend to react rather than like be available like in a biological setting. So this is an example of one of those. This is histrionicotoxin, histrionicotoxin. I believe it's a nicotoxin, and then you put histrio in front of it, which is a type of poison that's found in a certain species of frog in South America, just one of about 1,000 alkyne products. So they do exist in nature, and they can be synthesized by your enzymes, for example, or living enzymes, but they're much, much rarer compared to alkenes. Um, they're also very useful in a synthetic regard because they don't show up in biology. That means they don't really react with a lot of your biology, or I should say, like they don't interfere with the way that um, the way that your receptors work, generally speaking. So you can kind of stack it on to different compounds and have a compound that then mimics a natural effect. So the most common one here is what's called ethynyl estradiol. So this is estradiol here, and this is an ethyne group here, right? 1, 2 carbons, triple bonded, so it's ethyne. Think of it like ethynyl, it's the substituent onto estradiol. Estradiol, of course, is like a female sex hormone, and ethynyl estradiol basically mimics estrogen in the body, and so it can be used for things like menopausal treatment, like hormone treatments, and then also birth control pills because it mimics the sex hormone work. Okay, so that's where alkynes. That's how alkynes interact with us. Of course, we want to learn how to name them, and really good news here, guys. Alkynes are even easier to name than alkenes. If you know how to name an alkene, you can name an alkyne. Basically, like you're going to have a triple bond, right? So you're going to have a CC triple bond. That's going to be in the parent chain. Okay, then you identify and name the substituents, give a number to each of the substituents, and number the CC triple bond lowest possible. Again, the only thing we're changing here from alkenes is we're just replacing a CC double bond with a CC triple bond. Then you list the numbered substituents before the parent name in alphabetical order. And then you are going to go ahead and number the CC triple bond either just before the parent name, or if you recall, like what we were doing with alkenes, we would put it just before the ENE suffix. Well, with alkynes, same deal, it's just before the YNE suffix. So pentane, right, becomes pentene, and this would be pent1-ene because it's starting from this side here. And this is pentyne, and again, because it's starting from the first carbon, this would be pent1-ine. Yeah, so again, and this is just kind of like walking you through. So you identify the parent chain and make sure that you include the CC triple bond. Then give a locant, and then so like a number for each substituent, and give the CC triple bond the lowest number possible. So rather than starting from the right side over here and giving this a 5-ine, we know that we can start from the left and we give it a 2-ine in this case. So just again, that's exactly the same as what you did for alkenes. The only thing we're changing is we're changing the E to a Y. Then finally, no trick here, you're gonna list the numbered substituents before the parent name in alphabetical order, and then you give this, you basically use that numbering scheme for the triple bond. So again, the preferred route is gonna be down here, 5,5,6 trimethyl hept 2-ine. And again, it's totally fine, like on the exam here, if you get 2-heptyne, I'm not gonna count it wrong on your final exam. But it's just something to keep in mind for next semester. It's better to get in the habit of using the lower one here. Let me just circle it. So get in this habit down here because next semester you're going to have things that are alkynes and alcohols. And it's going to be confusing if you try to put the numbers at the front. So the numbers at the end are going to make a lot more sense for reasons that will become clear. Okay. Now, sometimes you will see common names. I won't be necessarily testing you on this, but it may be something that you see in the real world, so it's worth mentioning here. Acetylene is like the basic, it's one carbon triply bonded to another, and they both have a hydrogen attached, C2H2. So sometimes you will see these alkynes named as like derivations of acetylene. So this would be, for example, if you stick a methyl group on one side, it becomes methylacetylene. Or if you could put 2 isopropyl groups, it would be diisopropyl acetylene. And then finally, you could have phenylpropyl acetylene. That's where you have a phenyl on one side, a propyl on another. Again, I'm not going to expect you to do that for me, but it just may show up every so often in the real world. So I want you to be aware of that. Oh, and a very important thing here, one thing that we need to do is we need to be able to classify alkynes based on where they are located in the molecule. If they're on the end of a molecule, we call that a terminal alkyne. And this is important. A terminal alkyne is always going to have a hydrogen attached to one end. And this hydrogen has very particular properties. So like when we talk about a terminal alkyne, there's going to be a certain type of chemistry that can occur with a terminal alkyne that cannot occur with an internal alkyne. So we just want to make sure that we're kind of aware of that when we see this terminal alkyne. Remember, that means that it's got a proton attached to it. And not to give too much away, but this proton is relatively acidic compared to what we've learned so far. So that's kind of something to keep an eye on, make sure that you're aware of. Okay, so definitely practice with the nomenclature. I'm not going to do much more on this video, but if you go into the practice PDF, give that a try, and let me know if you're having trouble with that. The other good thing about alkynes is that there's no easy nomenclature. It's just there's no stereoisomerism associated with it, so you don't really have to worry about E or Z configurations. Okay. Oh, so this is kind of giving it away. Like, why is terminal alkyne? Why does that matter? It's because they have a very low pKa relative to what we've seen with the other hydrocarbons. So like if you go to ethane, ethane has a pKa of 50. That is not acidic at all. Ethylene, only slightly more acidic at 44. Now, so this is not acidic at all either. But acetylene, on the other hand, has a pKa of 25. So based on, remember, if this jumps by 19 pKa units, that means it's 10 to the 19th time stronger of an acid than ethylene. So that's a huge jump. And in fact, that does have implications for the reactivities of these terminal alkynes. So, and in particular, what you can do is you can take an acetylene or any terminal alkyne and you can deprotonate it using a strong base. So if you use a base that's stronger than the acetylide ion in this case, so it's just a stronger base. It's the conjugate base of a weaker acid, you could say. You can deprotonate this and form this acetylide ion. Now this is going to be important because when you have an acetylide ion, that's a lone pair on a carbon, that means that you have a nucleophilic carbon. So you can do some fun reactions with that, substitutions, additions, etc. Okay, so oh yeah, so talking about like why is it that acetylene is more acidic? Well, think to the conjugate bases, right? The REO method tells us that we need to look at the lone pair that's left over on the conjugate base, and based on what atom it's on, whether it has resonance, the inductive effect, and then what orbital it's in, that's going to determine the stability of the conjugate base, which determines the acidity of the proton. So if you have here, ethane versus ethene versus ethine, well, you're comparing the conjugate base. You have an sp3 orbital, you have an sp2 orbital, and you have an sp orbital. Well, O for orbital tells us that the more S character we have in that lone pair's orbital, the more stable that lone pair is going to be. So this lone pair in an sp orbital has 50% S character, whereas sp2 is 33% and sp3 is 25%. So with that increasing S character, we're going to increase the stability of this lone pair. So that's why that acetylene or any terminal alkyne is going to be much more acidic than any similar hydrocarbon. Okay, so yeah, so again, just if you have so you can use any base that has its conjugate acid, which is higher, the pKa has to be higher than that of acetylene, but practically speaking, we pretty much just use sodium amide here. So that's NaNH2, so this is NH2 minus. You've seen this before. We've used this as a very common strong base, and it's very convenient here because you just are able to deprotonate these terminal alkynes very frequently. So just keep that in mind. If you have a terminal alkyne and you see, oh, it's reacted with NaNH2, that's a way that deprotonates it and gives you the acetylide ion here. Keep in mind, like if you tried to use hydroxide, remember, hydroxide is not as strong a base as sodium amide. So that means that like overall, you're just not going to be able to deprotonate this, this terminal alkyne effectively. So you need a strong one, and that's why we use sodium amide almost all the time. Okay, so yeah, so again, any suitable base works. Practically speaking, we're going to be using sodium amide. And yeah, you can kind of like look at it here and how that works. One reason that we use sodium amide is because anything above it is kind of like hard to get to. You have these carbanions here. You also have hydrides. Hydrides you can use, but they're kind of hard to come across. So NH2 minus is just something that's relatively easy to store, and you can use it to easily deprotonate alkynes. Okay, so that's like one of the main reactions. And we'll talk like what can you do with the acetylide ion later in the chapter. There's a particular type of reaction that's very important. But for now, let's go ahead and talk about how you can actually make alkynes. So preparation of alkynes. So alkenes, you know that you can prepare alkenes from elimination of an alkyl halide. And what happens is you take your alkyl halide, you undergo an elimination reaction, you get your alkene. Well, you can do the same thing to make an alkyne, you just need to do it twice, okay? So you take, rather than alkyl halide, take an alkyl dihalide. You do an elimination reaction once, that gives you the alkene. Do it again, that gives you the alkyne. And then something to keep in mind is that there's two different types of dihalides that you can have. We have what are called geminal dihalides and vicinal dihalides. We talked about these words geminal and vicinal very briefly in the NMR chapter. We talked about geminal protons and vicinal protons. Geminal, we think Gemini or the twins, right? Geminal means that they're all on the same carbon. So if you have a geminal dihalide, that means both halogen atoms are bonded to the same carbon. And so when you do an elimination, you get your alkene, then you do another elimination, exact same mechanism, you're just producing your alkyne. For the vicinal dihalide, that means they're like on neighboring carbons here. You basically get two different eliminations. I can kind of like take a moment here. So if we take our strong base here, we do our first elimination, and oops, sorry, undo, there we go. There we go. So we do our first elimination, we create our alkene. And so we have R up here and H down here. And our bromine is left up here, and our R group is down here. And then you take your second equivalent of base. Basically, you chuck in a bunch of base, and this is what's going to help you move this reaction forward. And then you do your second elimination on the other bromine here, and that's how you get your alkyne there. So again, the mechanism should look very familiar. It's just the E2 mechanism. It's just showing that, oh, you can do it twice if you have a dihalide. And again, it can be geminal or vicinal. It doesn't really matter. I hope that word kind of makes sense. Right. And again, as I mentioned in the previous slide, if you use excess amounts of sodium amide or whatever your strong base is going to be, that's a way that you can shift the equilibrium towards the products. And basically, the reason for that is you form this alkynide ion. This alkynide ion then can't undergo addition on the way back, so you get your alkynide. Now, once you have your alkynide ion, you just need to note that if you put it in any protic solvent, so like water or ethanol, that's enough to then protonate it, and you get your alkyne, your neutral alkyne. Yeah, so like this would be what it would look like overall. If you're going to make a terminal alkyne, you have a dihalide here. Use your excess sodium amide and your ammonia. That's your solvent, right? So the reason that you have to use NaNH2 in NH3 is because you need to have a compatible solvent for the NH2 minus. If you put this in water, for example, that would get to the solvent or leveling effect, where then all of a sudden the water is going to react with the sodium amide, and you're going to just have hydroxide ions, which, as we talked about, not strong enough. It's got to be NaNH2 in NH3. And it's excess, so that means it's going to do two elimination reactions, and then you'll end up with the acetylide ion. Then to protonate it, you use the water molecule, and you're done. So yeah, that's how you prepare alkynes. If you have this dihalide, either geminal in this case or vicinal, where they're on neighboring carbons, then you can make an alkyne. Okay, so that does it for this lecture here. We're going to move on and we're going to talk about the different reactions that we have. We have two different lectures on kind of two sets of reactions that we'll talk about. And then we'll talk about different synthesis strategies later on. So take some time, look, make sure you can do the nomenclature, look at the first sets of reactions in the preparation part of the PDF, the practice PDF, and then we'll move on to the next lecture. So I will see you soon.